In this video, we're going to do example 7.6.3. X and Y are jointly distributed random variables with density function given here. And we're told that W is 1/2 x plus y. We're asked to calculate the variance of W in two ways. First, by using the computational formula directly, and using, in the second method, property 7 of proposition 7.6.5, and we're asked to verify that both methods give the same answer. So the first is the direct method, and so that is using the variance, the computational formula, as the expected value of W squared minus the expected value of W all squared. And these can be calculated as double integrals. So first of all, we'll replace. We have the expected value of 1/2 x plus y squared, and then minus the expected value of 1/2 x plus y all squared. So using the Lotus Theorem, we can integrate over this support, and so we'll have the double integral from 0 to 2 and from 0 to 2 of this function times the density. So 1/2 squared is 1/4 x plus y squared times the density, which is 1/8 x plus y, and dy dx dx dy doesn't matter because the bounds are the same for both. And then we have here another double integral, this time of this function, and that double integral, the value of the answer is going to be squared. So let's get that out here. And then so the double integral from 0 to 2, again 0 to 2. Now it's the function 1/2 x plus y times the density 1/8 x plus y dy. I haven't left myself enough room. Dy dx. So if I were going to actually evaluate this by hand, I would obviously clean up the integrands here and move some constants out and that sort of thing. But I've evaluated these off screen to save us a little bit of time. The first one gives us 3/2. The second one gives us 7/6, which needs to be squared. And if we compute that, we're going to get 5/36. So there's the first method, using the computational formula directly on the variance. The second asks us to use this property of 7.6.5, and that property was the following. I'll recall that for us. So this property was that if we had the variance of ax plus by, then we got a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance of x and y. So this was the formula in general. If x and y were independent, which we don't know here, and actually they're not, if they were independent, this term would drop out, but this is the general relationship for the variance of a linear combination of two random variables. So let's go and use this to calculate our variance of W. So that's the variance of, and I'll multiply through the 1/2 onto both of these so that we have exactly this form. So that's the variance of 1/2 x plus 1/2 y, which, using our formula here, is going to give us 1/4 the variance of x plus 1/4 the variance of y plus 2 times 1/2 times 1/2, or 1/2 the covariance of xy. Now each of these pieces has to be calculated using a computational formula using double integrals, and so let's write those out. So the first part would be 1/4, and the variance of x is e of x squared minus e of x all squared, and the same thing for y, so 1/4 e of y squared minus e of y all squared, and then the computational formula for the covariance is the expected value of x, y, no comma, the expected value of xy, x times y, minus the expected value of x times the expected value of y. So again, each of these pieces is a double integral. So for example, this one would be the double integral from 0 to 2, oops, not like that, from 0 to 2 and from 0 to 2 of this function times the density. So x squared times the density, which was up here, 1/8 of x plus y. So x squared times 1/8 of x plus y dy dx. And they are all calculated in the similar way, except instead of x squared, we replace x, or y squared, or y, or xy, etc., etc. So I've calculated all of these for us off screen as well. So 1/4 we got for e of x squared, we end up by getting 5/3. For e of x, we end up by getting 7/6, which needs to be squared. So plus 1/4 e of y squared. We could actually see this right away without calculating again because of the symmetry. This density function and the balance are completely symmetric. So I know that these are the same values that I'm just going to get back out for y, although I could obviously compute it as well if I didn't notice that, but that would save a little bit of a computation. This needs to be squared as well. And then lastly, 1/2 e of xy turned out to be 4/3. So you can take the time to do these computations if you want to and double check the answers that I'm getting here. So e of x, e of y, those are these two values which get multiplied there. And we crunch through and we're going to get exactly the same 5/36. So that is the same as in the first part. So whether you use the computational formula for the variance directly by using double integrals, or let's say you already had some of these pieces from prior calculations, you might want to use this property of a linear combination of variables to find its variance. Either of them, they will give you the same answer.